Hello, everyone, and welcome to today's free public webinar entitled Electrical Safety and Establishing an Electrically Safe Work Condition. My name is Ryan Smith, your host today, and we are joined by our presenter today, Bob Kluke, our TPC instructor. Bob has years and years of experience, decades in fact, of electrical experience as a master electrician, journeyman electrician, instructor for TPC, and done all sorts of things out there in the industry and in the field. We look forward to learning from him directly about the importance of electrical safety, in particular on the process of establishing an electrically safe working condition today. Before we get started and into the meat and potatoes of today's presentation, I want to just let everyone know a little bit about what they can expect after this webinar is over and what they can expect during this webinar. First and foremost, this webinar is being recorded, and we're actually going to be posting a link to this recording to our website within about 2 business days of today's event. So be on the lookout for that. You can watch it back with your coworkers and colleagues. The second thing I want to let you know is that you'll have a PDF as well that's downloadable on these presentation slides, so you don't have to worry necessarily about trying to take screenshots or anything. This will all be available for you to download afterwards. And then finally, this session right now is live and in the moment. So what that means is you can feel free to interact with us while you're here live with us. So you should see at the bottom of your toolbar a Q&A button. And that Q&A is for questions and answers. Feel free to type a question. It'll come to us on the panel, and we'll be able to answer your questions. And I'll be able to work on prioritizing your questions and organizing your questions for Bob. By the end of our session, we'll be able to answer as many of those as possible. So feel free to put them in the Q&A box. And with that, that's pretty much all the details of just how today's session is going to work. Listen in, use the Q&A box to answer and ask questions. And then finally, we're going to run a little poll before I close up my session here of the intro. We're going to run a little poll to learn a little bit more about who's here today. So what you should see showing up on your screen right now is a window asking 2 questions. The first question is, when performing a repair on electrical equipment, do you or your technicians perform the live dead live process? And say yes, no, sometimes, or you're not sure, because we got to learn a little bit more about it. And no problem, be fully honest here. And second, what is the highest voltage that you or your technicians encounter when you're performing live dead live? This is for those of you who did answer yes to the question above. Are you dealing with 120 volts and below when you do this process? Above 120 volts to 600 volts, or above 600 volts? So we'll give you just a few more moments to fill in your answer. You can just click the response that works best for you and click submit at the bottom, and it should be recorded there. Excellent. I think we're seeing the responses even out here. So I'm going to go ahead and end the poll. And I will share the results with you all. So what we are seeing is most of you, yes, you are performing live dead live, which is great to hear because it is an essential and necessary part to establishing an electrically safe work condition. However, there's still a varying level of comfort level around live dead live. A few of you don't know, and some of you are doing it sometimes, sometimes not, sometimes there. So we're going to talk about and break that process down in this webinar, as well as what is the highest voltage? So most of you, 67% of you, are working on voltages between 120 volts and 600 volts. So right there in that industrial and commercial voltage range. So I'm going to stop sharing the results. So what should have happened now is that the window with the results has disappeared from your screen, and you should see full screen Bob's presentation for electrical safety and establishing an electrically safe work condition. And without further ado, I'll give it over to Bob. Thank you so much for being here, Bob.
Thank you, Ryan, for the introduction, and thank everybody else for attending this session today. Hopefully you get the knowledge you want out of this session. And remember what Ryan said, if you do have questions, put them in that Q&A tab. And at the end of the session, Ryan and I will address as many questions as possible. So this, of course, is all based on OSHA 1910 and NFPA 70E. So we will take a look at what they have inside this document. This came from Chapter 1 in NFPA 70E, and it gives us a definition of the electrically safe work condition. So it's going to be a state, right? And that state is going to be when we have been disconnected from all energized parts. And then we lock and tag it out in accordance with your policy, because OSHA just says this. OSHA says we have to have a lockout tag out procedure, but it's up to us to come up with our own procedure that's going to work at our facility. And then we have to test it to verify for the absence of voltage. And we're going to go through an actual test today. I'm going to bring up a simulator that we will use. And if there is the possibility of the circuit becoming re-energized because of capacitance or induction, then we do have to put on ground straps. So that's just the definition, right? And but we are going to see these steps coming up. And then it comes down into when they really would like to see this electrically safe work condition established. And so if the voltage of our equipment, and this means that if any voltage inside of our cabinets is 50 volts or greater, then it says that our conductors and circuit pods shall be put into this electrically safe work condition, which we're going to look through all 8 steps coming up, before an employee does any work if they are inside the limited approach boundary. So from 50 volts all the way up to 750, that would be if the employee is within 42 inches of that equipment, or the employee interacts with the equipment where those conductors or circuit parts are not exposed. So we haven't taken any covers off. We're just going to do something maybe that the manufacturer allows us to do, but there is an increased likelihood of injury from the task that we're about to try to make happen. So for instance, maybe we're going to rack a breaker in and out of switchgear, or we're going to maybe stab on a disconnect onto bus duct. Those are all examples of increased likelihood that an arc flash could occur, and the technical committee for NFPA 70E believes we should establish an electrically safe work condition when we perform those tasks. So we're going to take a look at the steps now. There are 8 steps, and we have to make sure that we do complete all 8 steps. If we miss a step, it could be very dangerous for the employee who is performing this function. So the first step that we're going to look at is this: determine all possible sources of electrical supply to the specific equipment. Check applicable up-to-date drawings, diagrams, ID tags. So immediately we have to know this, that sometimes we don't have any drawings. Sometimes they're not up to date. In that case, we would have to walk down that circuit and try to locate all possible sources of supply to that equipment. And they have a couple questions for us here. What's the voltage of the circuit below, and are we qualified for that? So I like to zoom in so we can see it a little bit better. And we can see that if this was equipment in our facility, that it pretty much has one source of supply. It is 4160, so 4,160 volts, but the diagram gives us a great indication that we have that one source of supply. This happens to be a motor starter inside of a motor control center. So we have a disconnect with some fuses. We have some contacts in our motor starter. We have the ability to rack this in or out. And this is a reduced voltage motor starter. They're using an auto transformer to do this. But we can see here on this one, only one source of supply, which is really nice when that happens. We have to be very careful, because sometimes even checking diagrams, they might have that second source on a different print somewhere. I once saw a person was going to change a 3-phase 480 volt motor out, and he disconnected the motor. That was no issue. But there was another circuit in there. It was a heater circuit to keep the windings dry to prevent condensation, and he didn't lock and tag that one out and did not establish an electrically safe work condition on that second one. And unfortunately, that cost that man his life. So this is extremely important that we do identify how many sources of supply. If we have the diagrams, great for us. If we don't, then we got to rely on our experience, our coworkers. We've got to use our eyes. We have got to walk down where all those sources of supply would be. So the first step, we've got to know what the voltage is to begin with. Is our voltage 120 volts today, 208, 277, 480, or something above 1,000 volts? And that is all going to play a part in our process. So first we have to know what the voltage is and then how many sources that we are dealing with. Secondly, and there are two steps to this second little requirement here. It says after properly interrupting the load current. So what does that mean? That means that we're going to go up and hit a stop button, or we're going to go up and hit maybe open an interlock or whatever to get no current flowing through this disconnect that we can see right here, or the circuit breakers, or whatever we have that can de-energize that circuit. Why do we have to do that? We have to do that because this disconnect that you're looking at is a non-load break device, which means that with its UL listing, it is not made to be open or closed when there is current flowing through it, or when it's under a load. So we want to make sure that first we interrupt the current, and then we open this disconnecting means. And a couple things I want to mention on the disconnecting means, and I'm going to draw just for a second. So we'll take a look at this. I'm going to draw just a little stick figure here, and you can imagine that it's me if you want. I don't care. But here's what I want to tell you is that we always want to use our left hand when we pull this lever down. To begin with, that puts us off to the side. It's also very nice if we would fill our lungs up with air, just in case something bad happens here and there is the opportunity for an arc flash. We don't want to breathe in molten metal that got heated up to 35,000 degrees Fahrenheit. We don't want to breathe in toxic fumes. The medical community does have a very difficult time repairing the interior of our lungs. So if we use our left hand, stand off to the side, pull that lever down, and actually turn our back and take a step away, you'll be so far away from this disconnect that even if there was an incident that occurred, you would not have to worry about that impacting you. So important to understand on this one. First, we're going to interrupt the current flow. Secondly, we're going to open up that disconnecting means. So the first step, we're going to identify all possible sources of supply. Second step, we're going to make sure we open up that disconnecting means. Next, we'll go to our third step, which is extremely important. And again, I'm going to zoom in on this one a little bit. And what we have to do now is take a visual look. And we have to make sure that these blades that are in this disconnect have pulled out of those blade holders. And so this is a mechanical device. And at times, it could fail on us. And we do not want that to happen. So we're going to take a visual look. Now, with a disconnect that is about the size of this one, it's important. But when we get into very large disconnects at higher voltages, it becomes extremely important. I can tell you that I had a friend that was doing a job one time, and it was at 4160. He pulled the disconnect down, no problem. But then he never took a look in to see if all those blades did open up. And when he stepped into that, the electricity did arc over, caught his clothes on fire, third-degree burns over 40% of his body. So I believe our eyes are extremely important in the electrical trade, and we want to be looking at everything. Our eyes and our ears are going to give us clues. And so that's why we do thermography. That's why we do ultrasound. We want to make sure that everything is safe. So let's be sure that we are taking and looking at this visual verification. It does say wherever possible. So if it's a molded case circuit breaker that I can't open up and see the contacts, obviously I can't do my visual verification on that. But if it's a disconnect, or if it is switch gear with a window that I can look through, then I can look to see if we are still making contact or if we are open, which is extremely important. Next step number 4, release stored electrical energy. So I'm not sure how many people are aware of this, but in the 2021 version of NFPA 70E, we do have a brand new article, Article 360. It is on capacitors. So they are giving us some techniques on how to safely discharge capacitors. And they make bleed resistors that I can stab right over those terminals that will allow that to happen. They make a discharge wire with a couple insulated alligator clips that I can make the release of stored energy occur. We can also look at what the manufacturer recommends. If that capacitor is still connected to the circuit, sometimes the manufacturer will say, wait 20 minutes, and then you're going to have the capacitor will be completely discharged. If it's very high voltage, maybe some RF voltage with some cyclotron equipment or things like that, then they do give us a shorting stick. And we have to remember when we use that, that there's going to be a very high voltage, but not very much current behind it. So we might see a spark at times, but we are going to discharge that capacitor. So that was step number 4. Step number 5 is now talking about non-electrical energy or mechanical energy. So what does that really mean to us? It means this, that whoever is performing these steps, they have got to be very qualified on that equipment. They have to know how the equipment was constructed, how it was built. They have to know how the equipment was installed. They have to know how the equipment operates. And that is not just electrical, that's also pneumatic, hydraulic, springs, gravity, you name it. So there can be other energy present at some of these machines. And now we have to make sure that we're going to block that energy or we're going to lock that energy out. I can tell you that there was an electrician, highly qualified electrician, went into a facility, and he, he was very qualified electrically. Mechanically, he might not have known that machine as well as he should have. And so he had to work on his back. He actually had to lay on the floor and go under the machine on his back, and he's looking up when a 12-inch steel piston let go and came down and crushed that man's chest. And so, classic case where the host employer that he was working for should have provided this electrician with a worker from the facility that knew that equipment very well, because it cost that man his life because he did not know the mechanical side of it. So we have to be very qualified and determine the mechanical side also. Okay, the next step, we are going to put our lockout tagout device on in accordance with our policy. And so there is something that I really like to mention about lockout tagout, and I would love to have this part of the procedure. And I would like to say lockout tagout try. And so we're going to put our lock on it. We're going to put our tag on it. We're going to put our name on it or our picture and what time we locked and tagged it out. And then I really would like to see on that tag, did we try to start the equipment? Because many times there is lookalike equipment. So I really like to try the equipment that I'm working on, and so after we put our lock on, go up, hit that start button, whatever you have to do to get a um, a, a response from the equipment to see if it is going to work, try it and see if that's going to happen, because we can't take any chances that we did get the wrong equipment. This is maybe the most important step of all, and this is what out in the field we might call live dead live. Other names for it, I have seen in the OSHA standards, this referred to as the 3-point method. In the military, I've heard this being called known, unknown, known. In other parts of the world, test, prove, test. But here we do live, dead, live. And here's the process of this. And we're actually even going to be able to take a look at a little scenario with this after I've explained the whole thing. So first of all, they say this: use an adequately rated portable test instrument. So if the voltage that we're working on is 1,000 volts or below, we are going to have a multimeter to do this. We are going to actually make contact with that circuit. And those meters are rated in 4 different categories. We have all the way from category 1 up to category 4. Category 4 being the safest one we have. And those categories are protecting us from this. So if I have my sine wave, and then on top of my sine wave, I might see something like this, which we're going to call a transient or a spike, then these meters can only withstand uh, so high of a voltage. And so, for example, a category 4 meter can withstand up to an 8,000 volt spike without being destroyed. Also, a category 1 meter is going to be as low as a 2,500 volt spike. And so we have to have the right meter in our hand when we do this, because if these transients are present, they can destroy our meter. And a broken meter always reads 0. So I can tell you that it's very important that we do all of these steps, because if I keep seeing on my meter 0, 0, 0, I'm going to think it's safe to touch. But in reality, I could have a broken meter in my hand. And so we've got to be very careful about this one, and make sure this does not happen. Then it says, after we have the right meter in our hand, then we're going to test each phase conductor, phase to phase. So that's A to B, B to C, A to C, and then phase to ground, A to ground, B to ground, C to ground. So there's 6 tests. And then it says before and after each test, we've got to make sure that meter is working properly. So before I even start phase to phase or phase to ground, I'm going to test my meter on a known voltage to make sure that my meter is working just perfectly. And then when I'm all done, I'm going to test that meter again on a known voltage. I'll give you an idea why this is extremely important. Another example, both of the examples I've given so far, the first one and this one, are true stories. So this worker had to relocate a fairly large piece of equipment in his facility one day when he tested his meter on a receptacle. His meter said 120 volts. He went over to the piece of equipment. He went A to B, B to C, A to C, 0 3 times. A to ground, B to ground, C to ground, 0 3 more times. Never took that meter back to that receptacle. He saw 0 6 times. He felt very confident that his equipment was de-energized. Unfortunate to him, when he tested his meter on 120 volts, there were transients present that day. And unfortunately, one of those transients burnt out an electrical component in his meter, and his meter was broken. So his meter was not giving him an accurate reading. If he would have gone back and tested that receptacle again, he would have known that his meter was broken, but he didn't do it. He took an Allen wrench out, which was a uninsulated Allen wrench, put bare hands on it, put it right into a lug, and the man was electrocuted that day. He lost his life. So this is an extremely important step right here. Also, there's a couple exceptions to them. The first exception I have a few reservations about, but it is in here, and it does say that we can use an adequately rated, permanently mounted absence of voltage tester to do the same thing that we're going to do. This is going to be a meter that's going to be mounted right to the equipment. Meter never moves. It's always right there. And usually it's in the form of some lights. We don't actually see a voltage reading on it. We just see some indicator lights. And so it is going to be UL listed and labeled for this purpose. It is going to do exactly what we would do, test each phase conductor, phase to phase or phase to ground. It is going to verify itself that it works before and after, and we will see a picture of that coming up on the next slide. Exception number two, we do all the time. And so if we are at medium voltage, so above 1,000 volts, all the way up to 15,000 volts, they are allowing us to use a non-contact tester. So I would have a hot stick in this case. I would have my non-contact tester mounted onto the end of my hot stick, and I would test that before I did phase to phase or phase to ground. I would make sure that my non-contact tester was working properly, and make sure I tested it after also. So let's take a couple looks at maybe what some of this stuff looks like. And so we can see bottom left-hand side right here, that's where those lights are. And so this would be exception number one, right? It would be that this would be permanently mounted in equipment. And I have seen this permanently mounted in equipment. Green light indicates it's de-energized. Well, I understand that that is UL listed. It's allowed for us to do. But here's what my father told me when I was very young. Bob, nobody else is going to take care of you, so you better take care of yourself. And so I'm not sure I want to put my all of my trust in those green lights, but people do all the time. And then to the right, we do have a non-contact tester, and this would be used for over 1,000 volts. You can see that it would be mounted at the end of a hot stick. And so those I've used for a long time. And as long as we test them before and after, we should be fine by using these non-contact testers. I do want to mention that they do make a contact tester for voltages above 1,000 volts. It might not be as accurate as we like it, but I can tell you this, if I put it on 7,200, depending on how my connection is being made, how much pressure I'm putting on it, I might get 7,000, but at least I would know that there's a voltage there. But if there is no voltage, it would definitely say zero. So I could either use a contact or non-contact tester when I got above that 1,000 volts. This is the last step. And so the last step tells us that if we do have the possibility of induction or capacitance, then we have to put on what I call a grounding cluster. And this would be put on with a hot stick also. And so this is a temporary protective grounding device. It has a American Society of Testing and Materials standard, F855, that is going to tell us that it does have to have the capacity to be able to carry the maximum fault current. And it is going to make sure that if something does become re-energized that is out of our control, that hopefully we're going to open up an overcurrent device because we do have that circuit grounded. And so this is all going to happen, right, if we do have that possibility of induction or capacitance re-energizing our circuit, which happens a lot above 1,000 volts. And so we're going to place them in the proper placement. I'm going to give you an idea when I pull up the picture of how we do it. They are going to be capable of carrying the fault current. And of course, the fault current is the maximum current that the transformer can provide or a power source can provide. Normally, it would be a transformer. And that fault current can get very high. It could get up all the way up to 100,000 amps or more. So these have to be able to handle that. Again, there's the ASTM standard, and they have to have a very low impedance. So it does allow the operation of our overcurrent devices. And so these are going to be pretty much straight copper wire inside. Again, we would be using a hot stick, and we would be a little bit of ways away from the equipment, hopefully, depending on the voltage, at least 3 feet away. And this is how we're always going to put it on. This one here happens to be the one that goes on the grounding system first. So this would go on first with my hot stick, and then I would put phase A on, and then phase B, and then phase C. So now I've done all those procedures in front of me. I have taken a look to see how many sources of supply I've got. I have interrupted the load current. I have opened the disconnecting device. I've done my visual verification, released stored electrical energy and mechanical energy, put my lock on it, did live, dead live, and now I'm putting these on to make sure that if it does become re-energized, we are going to allow that overcurrent device to operate. To remove this, we go just in the opposite procedure. Phase C is going to come off first, and then B, and then phase A. Last to come off will be our ground connection. So important to understand that. Okay, so now we're going to do a little demo here. We're going to take a look at what live, dead live looks like, so we can see. And so just so you know, once COVID-19 hit, TBC training had to go to a lot of virtual training. And we have a lot of these different types of scenarios and different simulators if we are going to teach a class virtually. And so I am going to do the first two scenarios here, have some problems where we would definitely have to take a step back and look at those 8 steps that we just did again. I'm going to go to scenario C, which is going to just give us an idea how this should function, right? So first of all, I would want to make sure that my meter is adequately rated for the environment that I'm going to be doing this procedure in. For example, if I'm in an industrial or commercial setting and I am indoors, a category 3 meter could be used. That would give me a transient protection if it was 600 volt rated up to 6,000 volt transient. If it was 1,000 volt rated Cat 3, it would give me 8,000 volt transient protection. So I got to make sure I have the right category of meter in my hand. And so then I'm just going to turn my meter on. We can see it's saying 0 now. And the first thing they want us to do is test this on a known voltage. Well, no issue here, right? Because we have a receptacle. But there are times when I go up to some industrial machinery that I have done the first 6 steps, and now I'm on this step, and I have shut all the voltage off because what I de-energized was the machine that I'm actually trying to verify right now. So I can purchase a voltage sourcing unit. Many manufacturers make these. They come with a magnetic strap that I could actually hang this voltage sourcing unit right on the equipment. It will give me 240 volts AC or 240 volts DC wherever I go. And that would test my meter on a known voltage. But in this case, we're going to use this receptacle to go ahead and test our meter on a known voltage. I like putting the common lead where our neutral conductor would be on that receptacle. And then I bring over my volt/ohm lead and put it on the energized conductor. And we can see this receptacle is working just fine. So, which means my meter is working perfect. So I know the voltage on a receptacle is going to be 120 volts. My meter tells me 120 volts. So I've done the first step very well. I have determined that my meter is working properly. Next, I'm going to go phase to phase. So I'm going to go from phase A to phase B. I can see I have no voltage. So somewhere upstream of this, because normally we know that I'm going to have to, if I'm going to do something inside this disconnect, which my task today is going to be verify all of these connections are properly torqued. And so that means I have to have the line side de-energized also. So I had to go upstream to shut the circuit breaker off, lock and tag it out. I did all that where these conductors originate from. And you can see, pretty good job because we are at 0. So A to B is 0. Then we come A to C. That one is 0. And B to C is 0. So that's good. So phase to phase, we have 0 3 times. Now we're going to go phase to ground. And C to ground is 0. And B to ground is 0. And A to ground is 0. So that is perfect. We are next going to verify our meter is working properly again. So we're going to bring it over to this receptacle. And sure enough, we can see that the meter does work properly. So we could hit continue. And would we proceed with the job? In this case, yes, we would. And so you can see this gentleman getting out some 1,000-volt rated tools. He's got some proper personal protective equipment on. And so he should be very safe as long as he went ahead and did all of his 8 procedures that we have to do to make sure that it is in an electrically safe work condition. So I can remember starting in the trade in the early 70s, and my supervisor told me, test before you touch. That's about all he ever said. Gave me a little meter and said, if this thing illuminates, don't touch it. And I said, great. Well, we've come a long ways since then, right? We now are guaranteeing that our meter is going to work properly. We are going to test phase to phase and phase to ground, make sure it works properly after we do all that. And then we can go ahead and do our repair on that equipment. So those are the 8 steps. And so now I'm going to turn this back over to Ryan, and we will take care of any questions that you might have during this time.
Thank you so much, Bob. This has been very educational for me as well. Just rehashing these 8 steps, because man, if you miss even just one, your life could be in jeopardy. And so I hope you all found this just as illuminating and refreshing for you to really know these crucial 8 potential steps you might have to follow, and you will have to follow, to make sure your circuits are verified and de-energized. Now, what we're doing now is the Q&A session. So we have a few questions coming in now, and this is the time where I welcome you to put your question in the Q&A. If you have one curiosity or question for Bob here, then now is our chance to answer them in the next, I'd say 10 or so minutes before we wrap up for the day. So before we do, just to let you know, we're a phone call away and an email away if you ever want to ask more questions about the topic and how you can continue learning more. Obviously, we can only cover so much on electrical safety in just 1 hour. There's all sorts of other stuff about specifics of PPE requirements and really what voltage is and how to read it, and amps and alternating versus direct current and all that fun stuff to learn about in the classroom. So Bob might be the one you'd talk to if you end up taking an actual class to get the official certification on this. I think a couple of you asked if you're getting a certificate from today's webinar. Since this is a free public event, you won't be offered a certificate, but you can watch the recording back if you want to continue sharing this with others. Definitely recommend, again, taking a class. And the last thing I'll say about that virtual skills module you saw, those 2 other scenarios are really fun learning opportunities, and maybe get your heart rate rising if you make the wrong decision inside of these to really hit home some key lessons. So if you want to be playing around more with these, you can either take Bob's class and you'll be spending more time in the simulated environment, or you can contact us and we can get you access to try it out for yourselves. So with that being said, let's address one of the first questions here, and that is emergency lighting circuits, Bob. We got, this individual has an emergency lighting circuit feeding multiple areas. Should that still be turned off if we're working on that circuit?
Not only should it be turned off, but it has to be turned off according to OSHA 1910. And so lighting, unfortunately, has been very dangerous for us over the years. And there's still plenty of magnetic ballasts out there, still, believe it or not, which are going to increase the voltage up to about 6 times what the voltage is coming in. So that 277 all of a sudden becomes 1400 volts. But even if it's not that, even if we've um, renovated to LED lighting, then still we've got a voltage that is above 50 volts. And OSHA tells us that now with emergency lighting, we're definitely going to have two sources of supply. We are going to have the backup source, which sometimes it might come from a battery, sometimes it might come from um, a generator, just whatever our backup source is, and we're going to have the regular source. Both of those are going to have to be locked and tagged out. But what has helped us with emergency lighting is in 2008, they did give us a requirement that if there is a ballast in that circuit, whether it's electronic or magnetic, that we now have to have a quick disconnect in there. And we're going to open that quick disconnect, and it is going to um, de-energize all possible sources of supply going to that fixture. So that should help us. The only problem with that is that everybody does not have those quick disconnects. Because if your light was installed before then, or if your light was even installed during that little time period, some electricians didn't know what that was for at the time. And so they went back to their old habits. And so they cut them right out and just wire nutted the ballast in there. But I can tell you, even in 2016, there was a person working on an emergency lighting circuit, and they did not de-energize that circuit, and that happened to be in New Jersey. And unfortunately, that person received a shock while he was on the ladder. The shock did not kill him, but the fall that he had did kill him. So emergency lighting circuits are very dangerous. If we can keep the voltage below 50 volts, then we're going to have no issues. We can do whatever we please, and we're not going to have to establish an electrically safe work condition. That was a great question.
And to clarify that question, it looks like they're working in a hospital situation. Do the same rules apply there?
Yes, sir. Even in a hospital. In fact, the little story I told you about the person changing the ballast occurred in a hospital in New Jersey. And the citations for that were up over $170,000.
Wow.
So,
So even though there is life safety here, as they spell out in NFPA 70E, still the kind of the rule applies that you shouldn't be putting yourself in.
one of the few times
Mhm.
that OSHA is going to override life safety or any other safety. Under no circumstances does OSHA allow us to work on lighting circuits while they are energized. And so if that circuit has a ballast in any way, shape, or form, they do not want us working on that circuit energized. We would have to bring in another lighting source. If it was a hospital, then I'm going to have to bring in battery powered lights, give them the proper light they need, and to allow them to do their work. And so that would be all part of a risk assessment, and knowing that you know, let's face it. I mean, somebody could die today. Is it going to be me or somebody else? We don't want anybody to die. So if I've got to de-energize, then I'm going to make sure I have another source of lighting, and nobody's going to die, me or the person that we're trying to keep alive.
Thank you so much, Bob. Um, I saw this question come in right before you had actually brought us into the disconnect in that live dead live scenario, where I think you answered this question. But if you want to just hit it home, and this question, it goes as follows. When you open the disconnect, there's still voltage on the incoming side or the line side of that disconnect. How do you deal with this if you were going to work inside such disconnect? Do you need to work with voltage on the inline side of a breaker, or do you need to find a way of switching the inline voltage off before working on the enclosure? And it sounds like the latter is true, isn't it? Where we got to find something upstream of that disconnect if we're going to work inside of that disconnect. Is that right?
So that is true, Ryan. That's 100% true. That if our task involves us doing some type of repair inside that disconnect, changing a fuse is a repair. then I am going to have to go to the overcurrent device that is feeding that disconnect, and that's where I'm going to do my lockout tag out. And I've got to verify that those line side connections are all de-energized. So that's another great question.
Excellent. Um, Here's maybe a chance to have a little fireside chat moment there, Bob. Someone who's pretty new to the electrical trades and they're quite frankly scared to deal with electricity. What would you tell this person who is pretty scared overall to start working with electricity?
First thing I would say to this person is continue being scared. We have to respect the fact that there is some high incident energy out there, a very high fault current, and that at any time one of these incidents could occur. So to begin with, that's what we have to respect this electricity and understand that shock is the number one killer in the electrical trade. So we're going to make sure we protect ourselves from shock. We've got to gain some experience, though. If we want to stay in this trade, right, we have got to gain some hands on experience where we can interact with this equipment and do risk assessments to keep ourselves safe. So, for example, if I have to take a cover off a main distribution panel, then I'm going to do a risk assessment. I am going to do things like this. Well, how heavy is that cover? Is it going to take two people? Maybe it's going to take three people, one on each side and one person uh, bringing the screws out so I can get the cover away from that equipment. And we just have to gain some experience so that we're comfortable and we know where we can touch and where we can't touch. We know the techniques that we're going to need to do to keep ourselves safe. And so, if you do have a fear of being injured in this trade, that's perfectly normal. I still do. So I've been doing this since 1971. I still have a fear, and I always say to myself this: that's just like a 30-06 with a hair trigger. It could go off at any time, and I could show you video after video after video where explosions have occurred where the person's not even interacting with the equipment. And so we just have to be on top of our game all the time. And experience is something that we really can't put a price tag on. And your experience might start with 24 volts, something that you can practice with a voltmeter. And we know that there's going to be no chance of an injury if we're just using 24 volts. And so that would be the place to start. Maybe get some 24-volt equipment, motor starters, relays, uh, timers, and start building circuits and testing it and just becoming familiar with how to use a voltmeter, ammeter, ohm meter, and then graduate up to maybe 120 volts after that. But learn the personal protective equipment you're going to need to keep yourself safe. Another great question.
Absolutely. I got just a couple more questions coming in here. Um, One question is about some terminology here. I think particularly about that last step of the process of grounding. Um, so how do how do we check for the term earthing? And is there a difference between the term earthing and grounding? That's definitely a new term for me, the term earthing. And would you like to differentiate between those two, if at all?
So when we talk about grounding and bonding, which is Article 250 of the National Electrical Code, here in the United States, we are going to call it um, grounding, and that is going to be a connection to Earth. And why do we do that? We do that to make sure that we can dissipate lightning strikes and to stabilize our voltage under normal operations. And so that's why we make that connection to Earth. In other parts of the world, they call it earthing, where we actually connect to the Earth through a grounding electrode, and we hope that is a very low impedance path to allow our overcurrent devices to operate. But we have so much more than just that term, because then we have to bring that connection to our equipment. We're going to do that with an equipment grounding conductor, which is going to be green or green with one or more yellow stripes on it. And Then we're also going to ground our neutral conductor at our service. And so we call that a grounded conductor. And so we have 2-day seminars on grounding and bonding that are very technical, but basically, earthing and grounding is a connection to earth. We are making a connection to earth through a grounding electrode.
Excellent. So I think one of our final questions coming in here is, and this, I think it's a short question, but I think it speaks to a lot of the curiosities from our customers. And that is, do you need to be a licensed electrician, Bob, to change a light ballast? How would you comment on that?
No, no. So what you have to be, though, is qualified. So qualified in the eyes of OSHA is a very powerful term. Only the employer can qualify a person, and that employer can qualify a person on different tasks, multiple tasks, or maybe the whole facility. And so basically, qualified means that we know how the equipment was built, how the equipment operates, how the equipment was installed, and has that person received some safety training to be able to keep themselves safe, and can they do risk assessments? And so TBC can assist employers in that process. Every employer has to have a procedure on how to get their technicians qualified, and that procedure could be different from every employer in the United States. But they have to be able to demonstrate that they can do certain tasks safely with that equipment. So part of the process of qualifying somebody is going to be a hands-on process. They have to also give us an indication if they understand all of the procedures. So that could be a question and answers session, it could be a written test or whatever. And then they've got to make sure that they have had the proper safety training. And so if a person is qualified, if the employer has deemed that they are qualified, maybe they're only qualified to work on injection molding machines, but they're really good at that. Or maybe they're qualified to work on injection molding, extruders, switchgear, motor control centers, AC and DC motors. It just all depends what that experience of that person is, and if the employer feels comfortable in qualifying that person. And so any task in the electrical trade can be done without a license if in fact you are qualified by your employer. Licenses, though, are going to really be for the construction trade. In other words, if I'm going to build a new office building somewhere, I have to pull an electrical permit for that. And to pull that permit, I would need a license. But to actually work in a facility and work on their distribution systems or their equipment, then I only have to be qualified.
Got you. So I bet you were just waiting for a simple yes and no out there, but it's a lot more to it than just can you or can't you. There's a lot more behind that in terms of being qualified. I think the last question we have for you today, Bob, is this is again a very specialized scenario, but feel free to comment on this one, and that is a hurricane situation in this individual's facility. Their facility requires that the primary feed for the building transformer has to be turned off during that hurricane situation. Should this be done by hand or with a pole to throw the disconnect? Any thoughts on that before we close up for the day?
With a pole.
With a
So
pole.
with a hot stick, and that's going to be the safest way to do that, especially in a hurricane situation. We're not 100% sure of if the equipment has been able to withstand that environment. And so we want to be as far away from that uh, transformer as possible. And so if I have to go to a cutout on the pole, I want to use a hot stick to do that.
Excellent. Well, thank you all so much. Thank you for being here, Bob, and sharing your knowledge with us today. And thank you all for being here with us today as well. We actually have another webinar coming up right after this one, so stay tuned. In 30 minutes from now live, we have one all about fuses and circuit breakers and how to understand and work on them. So feel free to stick around for that and register on our website if you haven't already. And we will see you all soon. Thanks so much for being here.